All right. Well, thank you, everybody. Thank you so much for coming to the talk tonight. I'm planning on talking probably for about 75 or 80 minutes or so. I have a tendency to run a bit long, so we'll see. But I am going to stick around for questions, and you all know where to find me online and everything. I just started a Patreon as well, so if you like the way I talk about this, you can hear more stuff like this as well later on. So outline for today, we're going to talk about the physics of global warming, and then we're going to talk about some of the really obvious threats of global warming, the really scary stuff, the things that people are worried about, why they want to stop it. And then in that vein of these really scary things, I'm going to talk about sort of a long shot technology, negative emission technologies, a family of technologies, things that suck carbon dioxide out of the air. And the second long shot technology I'm going to talk about is geoengineering, solar geoengineering, also called solar radiation management, essentially blocking the sun to artificially cool the planet. So these are sort of the extreme things that we might think about doing in the future when global warming gets even worse than it already is. And of course, as you can tell from the title and from the description here, I'm going to talk about why I think these things are going to fail. I'm going to be very critical of them, and I'm going to say that really the only thing we know that's going to work is going to be decarbonization, moving the whole economy off of fossil fuels, everything that emits greenhouse gases, ending all of those things. So what controls Earth's temperature? So everything in the climate system starts with the sun. So the sun on the left-hand side of your screen, I'm going to use my mouse here. It all comes in, and about 30% on average over the course of a year of sunlight gets reflected back into space, either by stuff in the air, by clouds, or by dust, or by bright stuff on the surface, things like ice and snow, stuff like that. So 70% of incoming sunlight that hits the Earth is absorbed, 30% is reflected back to space. As the planet is heated up by the sunlight, by trapped radiation, it warms up, and so it re-emits in the infrared band. And so we're all emitting infrared radiation right now. If you're sitting in a chair, that's emitting infrared radiation. If you went outside, the trees are emitting infrared radiation. The street is emitting infrared. The buildings are emitting infrared. Everything emits infrared, and it heads up into space, which is what the second set of arrows is here in the middle of the graphic. So you can see infrared radiation going up into space. And if we didn't have an atmosphere, if we didn't have what's called greenhouse gases, that outgoing infrared radiation would just escape into space. And the Earth would be much, much colder. So we wouldn't trap that heat anymore, that radiative energy. But it turns out we do have an atmosphere, and we have greenhouse gases, and those greenhouse gases are able to see infrared radiation and absorb it. So they absorb infrared radiation and they re-emit infrared radiation. And that's what's happening here in the middle. It's trapping that infrared radiation, and it's sending radiation down to us and away up into space. So this back radiation term here in the middle of the figure is what makes life on Earth possible. It's what keeps all the water from not just being frozen all the time. But it turns out that not all the radiation that's going up into space is captured by the greenhouse gas layer. A small sliver of it actually escapes the greenhouse gas layer through what's called the atmospheric window. So that's this little sliver here. So the atmospheric window is a piece of the infrared band that's invisible to the greenhouse gases. And it turns out what we're doing is human activity puts more greenhouse gases into the atmosphere: carbon dioxide, methane, nitrous oxide, fluorinated gases. As we put these greenhouse gases into the atmosphere, it closes the atmospheric window. So less and less of this radiation that used to be able to slip into space is able to slip into space, and more of it is captured within the climate system. So there's less outgoing, and there's more downwelling radiation now. So we're strengthening this blanket around Earth's climate system, and we're not letting as much infrared radiation escape to space as we used to. So that means that energy is building up in the climate system. And that's what we call global warming. So there's a few greenhouse gases that human activity emits, but far and away the most important is carbon dioxide. So this is a really cool graph of atmospheric carbon dioxide levels in parts per million going back 800,000 years. So this is a record that combines two things. It combines the ice core record from Antarctica going back 800,000 years, and on the far right-hand side, it combines observations at Mauna Loa that have been taken since 1958. So you can see this really cool up-down pattern in CO2 going back 800,000 years and even farther if this data set could see that. So this up-down pattern reflects the ice ages. When CO2 is high, that corresponded to times when Earth was relatively warm. When CO2 was low, that corresponded to the ice ages when Earth was relatively cold and there was much more ice on the planet. So this up-down, you can see CO2 bounces between maybe about 180 parts per million to about 260, 280 parts per million, this up-down. And not every ice age is the same. So let's go all the way to the right-hand side of the graph. So this is the last 10,000 years. The last 10,000 years are called the Holocene. And so this is a time in Earth's climate history when the climate was relatively stable. So this stability of climate in the last 10,000 years is a really important thing that allowed human civilization to flourish. You know, it let us start agriculture. You know, it let us build cities, complex societies. And a lot of the foundation of that, of course, was because climate was relatively stable. And so you can see what happened in really just the last 60 or so years, but you know, since the start of the Industrial Revolution. We are in this Holocene where CO2 is relatively stable, and just in the last 250 years, we've added CO2 so quickly relative to the geologic record, it looks like a vertical line. So that is what human activity has done on the right-hand side of this screen, really in, you know, mostly just 70 years, kind of the post-World War II boom in the fossil fuel economy. So we're adding CO2 at a rate that, you know, might be unprecedented in the geologic record, incredibly fast. And we're leaving behind this climate that human civilization grew up in. All these complex societies for thousands of years have relied on this relatively stable climate. We're throwing that all away. So as we add more CO2 to the atmosphere and other greenhouse gases, more and more radiative energy gets trapped in the climate system. That gets converted into heat, and that heat goes all over the climate system. It gets trapped in the ocean, it melts ice, it warms up the ground, and of course, most important to us, it warms up the air, and that's what this shows here. So this is a graph showing change in global average temperature, near surface temperature, 1850 through last year. These are annual averages. So you can see sort of through the middle of last century, there's a gradual rise in temperature. And then in the second half of last century through the present, there's a very steady increase in temperature. Temperatures have increased so much, they're now about 1.2 or 1.3 C above the pre-industrial average, the average before we started warming the climate. And you can see that the two warmest years on record are 2016 and 2020. So those are both El Nino years, which generally speaking are warmer than non-El Nino years because there's much more warm water in the Pacific exposed to the air, sort of a natural oscillation in the climate system. And so last year was not an El Nino year, so it wasn't able to break the record for warmest year on record. I think it was about the 5th warmest year on record in most data sets. But the thing to note here is that even though there's a little bit of natural variability in the system, the long-term trend, because of human-released CO2, is a very quick warming. And so the 7 warmest years on record have happened in the last 7 years. 2022 is not going to be any different. I think it's also on track to be about the 4th or 5th warmest. There's a very solid La Nina, which generally speaking are cooler years. And so usually what you can do if you sort of want a clue as to how to read the climate data, next time there is a significant El Nino is probably the year that we will break the warmest year on record again. So this is a little oscillation superimposed onto this linear trend of warmth. So where are we headed? So we've warmed 1.2, 1.3 C because of all the CO2 we've added to the climate system. Where are we going? So in the last big climate report, which is still coming out, I think there's one last section to come out, but it started coming out last year. The scientists came up with what are called SSPs, shared socioeconomic pathways. So this is a little bit annoying because in the previous reports it was called RCPs, or representative concentration pathways. But either way, both of those kinds of lingo, basically what they are is they are ways that human society uses energy in the future, possible pathways of energy use going forward. So you can imagine, sort of a low energy use future where we get off fossil fuels as fast as possible. We walk and bike and take public transit where we can. We stop using SUVs. And that's really these low scenarios here, the SSP ones down here. So these are the low fossil fuel use futures. So this is really, I think, an important thing about these is when they formulated them, and I think it matches up with the real world, is that these are futures where the world cooperates to move off of fossil fuels, right? There's not as much competition. The world works together on this huge global project. And as you go up, you have either less cooperation or more fossil fuel use, generally speaking. And at the very top is sort of an apocalyptic scenario where every country tries to burn all of the fossil fuel reserves that they have on hand. So what people come up with now is with these scenarios is that experts come in later and they say, okay, so this is sort of a guess at the best possible future and the worst possible future. Where are we headed towards in the middle of those? Where are we going? And what it looks like is that we're most likely headed for 3C, which is sort of above the 4.5 scenario in the current one. It was about the RCP6 scenario in the old one. So that's sort of the middle of the road guess. If somebody sort of told you where we're headed, it probably would be about 2.7 to 3.2 degrees C. That would be sort of the middle estimate of future warming by the end of this century, maximum warming. The best case, unfortunately, is 2C of warming. That's kind of the best that we can hope for at this stage. And the worst case, which is still possible, is 4C of warming. And a big thing about this 4C of warming, or possibly even above, is that it would rely on feedbacks in the carbon system. So, for example, permafrost thawing and releasing carbon and methane faster than we thought. The ocean stopping taking up as much carbon as it did. Wildfires getting even bigger and burning forests, peat bogs drying out and releasing their carbon. These are the sort of things I think that make the 4C or higher one a very small possibility. There's really a very small chance that they happen, but I think we cannot rule it out yet. Sort of a black swan, sort of fat tail, or not fat tail, but, the tail of things. So 2 to 4 degrees warming, I think, is where we're headed, with 3 being the best guess about. So we're adding all the CO2 to the climate system. It's warming up. What is going to happen as it warms? So this next section is going to detail like 5 or 6 sort of big threats that I think are really most dangerous from global warming. So the first, unsurprisingly, is deadly heat. And so that's what's shown here. So this was a nice study from 5 years ago that looked at increase in number of days by the end of the century for the number of days that led to the type of heat wave that killed people in the past, basically. So deadly heat waves. So the increase in the number of deadly heat waves. And so top left shows historical, and you can see these deadly heat waves have happened in the past with some regularity, unsurprisingly, in West Africa and India, Southeast Asia, Northern Australia, and some of the interior parts of South America, and a few, of course, places in North America and Europe, but much less. And as we go forward, basically the number of these deadly heat days goes up. So we're probably headed towards a future halfway between the two on the right. This is RCP, so this is from the old IPCC report. And so we're about halfway between these two. And you can see that the biggest threat is across the tropics and the subtropics. And, the thing that I like to point out about this is that there's tons of just enormous cities here. There's just so many people that live in all of these places that are in this bullseye of deadly heat going forward. Really, hundreds of millions of people are going to be living in places where these deadly heat waves are. And so, of course, things like air conditioning become a necessity. Not necessarily in the American way, but in a like elderly people and children who cannot cool their bodies sufficiently, will need it to get from day to day during these heat waves. I think a very important thing to note is that a lot of the times when you look at a climate projection, it's these smooth averages, right? But we don't move smoothly into the hot future. The future every once in a while sort of appears to us very sharply and very suddenly and horribly. And one example of that was the June 2021 heat wave in the Pacific Northwest. With a peak in Oregon and Washington and southern British Columbia. And so there was a number of really crazy and anomalous things that happened. And one amazing one was a coastal city in Washington broke its previous all-time record high temperature by 11 degrees Fahrenheit. So just really unbelievable. The hottest temperature ever recorded. That day, it was 11 degrees Fahrenheit hotter ever. So just really crazy. And so it turns out it was perhaps the most anomalous weather event in the instrument record. And the only one that was a contender was the heat wave in Russia in 2010, which was also a very horrible event. So the heat wave, as everyone knows, it killed and hospitalized hundreds of people. It made working conditions of all types really dangerous. It was so hot it buckled roads and broke bridges and train tracks because of the heat. They weren't designed for it. And that extreme heat dried out the forests so quickly and so severely, it led to a massive wildfire outbreak in British Columbia. And that smoke was living with people for a very, very long time. So this graphic here I'm showing is the highest high temperature of the year at Portland Airport at PDX. And you can see that the high temperature, I think the previous record was 42, but the high temperature is usually around 38 C. And then all of a sudden it was 47 C last year. So just a stunning event. Just really, really crazy. And this is a preview of stuff that's to come, right? We don't just move smoothly into the future. All of a sudden, we get these crazy previews of what the future will be. And so this event really scared me. And I think we're really just not preparing for this stuff fast enough. Another thing that's going to happen as we go forward into the warmer future is that the nature of precipitation is going to change. This is a nice graphic from an old climate report. So this was put out during the Trump White House, and so it was kind of published in a funny way. I think they sort of tried to slow it down, so I just remember it coming out as a draft. But this is change in the percentile precipitation in the continental U.S. So severe precipitation is on the right, and no precipitation is on the left. And this is so change in the end of the century compared to the end of last century. And you can see that severe rainfall is going to increase in the future. And this is a result you see across all kinds of climate models. It's a result that's held up by theory. And in fact, it seems like climate models are under-predicting just how much severe rainfall is going to get worse in the future. And so not only is severe rainfall going to get worse in a lot of places, sort of the moderate rainfalls are going to decrease, the nicer rainfalls, the kind of rainfall that a farmer would pray for. And eventually a trend will emerge where we actually have fewer days where rain falls. So we're moving towards this trend of really, really extreme rain. If people remember the pictures from Western Germany and Belgium, pictures from that city in China that flooded. I apologize if I forget the name, where the subway really horrifically flooded. Flooding in Tennessee last year, flooding from the tropical storm remnants in the tri-state area on the East Coast. These are the kind of rain events that we're tipping the scales towards. These are also a preview of the future. But even as we get these extreme rainfall events, the odds of drought go up because the atmosphere gets thirstier. So the warmer air is, the more water it can hold, and the more water it wants to steal from the ground. And so that thirstiness of the air is going to lead to more droughts in the future. And so this is from a very new study. It came out 2 months ago, looking at the latest climate model results. And what they looked at was just a bunch of drought characteristics in these model projections. And basically, in the path that we're sort of headed towards, probably a little bit worse than this, drought is going to get worse really pretty much everywhere. So the top shows an increase in drought frequency at the end of this century compared to the end of last century. And the bottom graphic shows a change in the length of droughts by the end of this century. So droughts happen more often, they last longer. They also will come on much faster, what scientists are starting to call flash droughts, droughts that pop up in the space of weeks. And one thing that's really dangerous, and an example of that is what happened in British Columbia that led to the fires, is what's called hot droughts. So in the future, when a drought happens, it's going to be 2, 3, 4 or 5 degrees Fahrenheit warmer during the drought, if not more so. That's going to demand even more from the trees, and the trees will dry out even more, or crops will dry out even more, and it'll do more damage. It'll make wildfires more dangerous in the follow-up to the drought. So really all characteristics of drought are likely to get worse in the future. Even as drought gets worse, unsurprisingly, mountain glaciers are also going to shrink, and they have been shrinking. So this is a really cool data set from the World Glacier Monitoring Service. It shows mountain glaciers from across the world and a global average with the dashed black line. And you can basically see that all mountain glaciers are shrinking and quite quickly. The ones that are shrinking the fastest are the Andes and Western North America. The pink and the orange here at the bottom. And the one I think that most people have their eye on is Central Asia, the Himalayas. And so the glaciers in the Himalayan plateau feed rivers that billions of people rely on. They provide summer base flow for so many people. And even under a low warming scenario, even if we somehow miraculously kept warming to 2C, a lot of these glaciers are going to disappear. A lot of base flow is going to disappear from these rivers. And of course, there's a long history of fighting over this water everywhere that relies on these kind of rivers. Places where they cross borders, it'll be even more contentious. And I think this is just a really important thing to think about going forward. Perhaps the sort of biggest thing on a lot of people's minds with respects to global warming and the ways that it will impact people in the biggest way is through changes in food production. So there's a lot of lenses to view it through, but I really like this study. It came out 4 years ago. And so what they did in this study was they looked at 6 major growers of maize, what we call corn here in the US. And they looked at 2 climate scenarios. So in black is maize production for these 6 regions in the present climate. So you can see there's natural variability, there's year-to-year variation in yield, but it's relatively contained, right? Plus or minus 20% or so for most of these. So what happens as you get 2 degrees warmer in blue or 4 degrees warmer in red is that the average yield decreases. So as corn gets warmer, generally speaking, it yields less. But more importantly, in what this study focused on, the standard deviation of year-to-year yield, the variability of year-to-year yield goes up dramatically. So compare, let's look at China, which is in the middle of the screen, the present climate on the right in black, and a plus 4C world in red. You can see that there is a non-zero chance now of almost total crop failure. The average is greatly decreased, 30 or 40%, but there's a significant chance of near total crop failure. And so the concern in this study, and the thing that people study, is simultaneous crop failures across the world. So you can imagine the US, Ukraine is on this map. Brazil, China, say they all had climate events that destroyed their ability to produce corn. All of a sudden, there's not enough corn for the whole world based on what it is. And so you can imagine this happening with other staple crops as well. Wheat, soybeans, rice. So the chance of simultaneous food production failures across multiple bread baskets will go up in the future. And this, for a lot of reasons, is really on our minds right now as well. So the last big threat that I'm going to talk about, sort of an existential threat really for a lot of places, is sea level rise. And I really, really like this graphic by Dr. Andrea Dutton. And what it shows is sea level rise for 3 different periods in the past and the present on the left. So basically what they show is CO2. So CO2 in the present has gone from about 280 parts per million to over 400 parts per million. This paper is a little bit older, so it's gone even higher than you can see it here. And at warm times in the past and interglacial periods, CO2 was about the same as it is today in these 2 in the past, but sea levels were much higher. So sea levels were 6 to 9 meters higher than today, 6 to 13 meters higher today, depending on your estimate and on uncertainty. And you can see that in the past, more and more of Greenland melted, more and more of Antarctica melted, and that's what's shown here on the bottom. And so basically what we're doing is that we are pushing CO2 to a level that is commensurate to a sea level rise, possibly on the order of 10, 20 or more feet of sea level rise. The reason that we're not going to see it this century is because these changes take a very, very long time to take effect. It takes a long time for glaciers to respond to warming, for the ocean to respond to warming. But basically, we have already put enough CO2 into the atmosphere to raise sea level on the order of 40, 50 feet or more. It's just a matter of the whole climate system having enough time to respond. So basically, we're on this path where the more CO2 we put into the air, the more sea level will rise, the faster sea level will rise, and all of the people that live on coasts, all the cities that are on coasts, they're not going to be tenable anymore, and it's likely that by the middle of the century, 150 million or more people live in places that will be underwater a significant amount of the year. At high tide during the year or during storms, flooded. So, you may be able to live there for some of the year, but some of the year you'll be underwater, and that's where we're headed towards. So the paleo record really shows us situations that just how extreme our CO2 increases are. The climate system just hasn't had the thousands of years that it's used to catch up to the sea level rise that should follow the amount of CO2 that we've put into the air. So to sum up this first section of the talk, global warming is going to mean countless changes for a lot of the U.S. But despite that, we're relatively wealthy. In some ways, we're shielded from a lot of these things. It'll probably still be a livable place in 100 years in many parts of it. But for a lot of densely populated parts of the world, they're going to become largely uninhabitable by the end of the century if we continue the way that we're going. And as it gets warmer and warmer, more of the globe is going to experience deadly heat, particularly in the tropics and the subtropics, but not contained to them. It'll definitely touch us here in the mid-latitudes as well. We're going to get flooding rains unlike anything we've seen before. Really extreme rainfall, really extreme flooding. Decreased soil moisture, increased odds of severe drought, decreased summer base flow of glacier and snow-fed rivers. We're going to get decreased crop yields and much higher year-to-year variability in crop harvests, and we're going to have greater odds of food shortages and rising food prices going forward. We're going to get higher seas, more storm surge flooding, and gradual groundwater penetration of salt water. So it's not just the water that you see over the ground, it's also the water beneath ground that makes near coastal areas become uninhabitable slowly and then sort of all at once. And of course, this is not an exhaustive list. There's other things that could be on here as well. So as it should be clear, by the end of the century, climate impacts like these listed above is going to make life worse for billions of people around the world, right? And wealthier people and wealthier countries are going to be better able to weather the storms to come. I think one really important thing to think about, something that I think we don't think about enough, is that a lot of climate change is permanent. It's here to stay. This is a really nice study from the 2000s from Susan Solomon and co-authors. She is one of the people that figured out the chemistry behind the ozone hole, so an extremely famous scientist at MIT. And she also did this excellent paper about a decade ago. And basically what they did is they looked at a really simple model, and they said, what happens in 1,000 years? What happens in 2,000 years to climate change? And so what they did was they put CO2 and they had it increase 2% a year, and then they stopped emissions. They said, what if emissions suddenly stopped? So let's follow these lines. Let's say you let emissions climb up to 450, 550, 650. I don't see us getting much higher than that. And say you cut them off immediately. CO2 sinks down a little bit, goes into the ocean, into the land over the course of hundreds of years. But the thing is, even after 1,000 years, CO2 is way, way higher than it was before we started emitting, all the way back, with the invention of the steam engine and combustion. So the CO2 that we're putting in the air now, some of it is going to be around for hundreds of thousands of years. Not all of it, but some of it. And that's just because of how slow parts of the carbon cycle are in the climate system, how long it takes the ocean and geology to respond to this huge pulse of carbon that we're putting into the atmosphere. So a lot of this CO2 is going to be around for millennia to come. And so even though CO2 goes down, an interesting thing happens, and that's that warming doesn't really go down in the future. So going forward, whatever warming we sort of end at, all else held equal, is kind of the warming that we have for about 1,000 years or longer, thousands of years to come. And so this, again, is a consequence of the ocean having a very slow response time to the radiative imbalance at the top of the atmosphere. So it takes a long time for the whole ocean to see the radiative imbalance and to warm up and to have the surface of the ocean communicate with the deep ocean and the top of the atmosphere. So a lot of the warming that we've done, it's here. It's here for good. And so this is a big reason why sea level rise is going to continue for millennia to come, because this warming has to filter through the whole climate system. This huge, fast climate change that we have done to the climate system that's faster than possibly anything that has happened in Earth's climatic history. So this is a huge bummer, right? There's all these things that is going to make life worse for so much people. And not only that, we're doing this change that's going to be here for not just centuries, but millennia to come. We've put our fingerprint on geologic history at this point. At this point, we've likely delayed the next ice age. The next ice age probably won't happen because we've put too much CO2 into the air. So the delicate orbital changes that trigger an ice age aren't enough anymore. It's just too warm. The ice sheets won't start to grow. So we've really started to change things, not just on a human time scale, but on Earth's time scales. So a very fair thing to say when someone tells you about all this stuff that is such a huge bummer is, I say something like, we're adding too much CO2 to the atmosphere. Why can't we remove it? Right? So that's a fair question. And so there's a whole field of study looking at these things that suck CO2 out of the air, these things that sort of try to hit the cause of global warming. And these are called negative emission technologies, or NETs. And so this is a list of the ones that I'll talk about in a little more detail. There's one called bioenergy with carbon capture and storage, or BECCS, direct air capture, DAC, accelerating the geological carbon cycle, enhancing the weathering of rocks, and what's called natural negative emission technologies. And so that's the things that you think of, like planting trees or restoring a bog, if any of you live in a bog, things like that. So let's go through a few of these proposed negative emission technologies and talk about sort of the big flaws in them, basically. So up to a few years ago, this was the huge one that people talked about. Bioenergy with carbon capture and storage, BECCS. And so this one played a really prominent role in CMIP 5, the last climate report. And a big reason that it played a role is because Sweden, I think in particular, wanted it included. And so, of course, they harvest a lot of wood. They're experts in forestry and things like that. So it's not surprising that they would want one based on bioenergy, perhaps. So either way, it's something that's on a lot of people's minds. So what is BECCS? How does it work? So this is a really nice graphic. And what it shows is BECCS starts with some sort of energy crop. So let's say, in this case, trees. And so the trees, as they grow, they suck up CO2. And so then what you do is you harvest the trees, say after 20 or 30 years. In the US, I think the kind of trees they talk about growing would be some sort of aspen, a fast-growing tree. And so you would harvest those trees. You would pulp them, probably, maybe make them into wood pellets, something like that, and you would burn them in a specially designed plant for bioenergy. And so you would burn it, you would get electricity from it, and before the emissions could leave, you would capture them at the smokestack, and you would capture the CO2. So you would get electricity, you'd get heat like you do from any power plant, and you would get this CO2 byproduct. And so the idea, generally speaking, is that you would pump that CO2 underground. You would liquefy it and pump it into some geological storage, which is shown over here. But some proposals also have it maybe being turned into some kind of synthetic fuel, something like that. So there's a bunch of problems with this, unsurprisingly, that are not shown in this very pretty little cartoon. It's unclear where the land would come from for these enormous energy plantations. So the trees that you would have, where would you plant them? If you all of a sudden had a need for tens of millions more acres of energy crops on top of the requirement for food, on the top of the requirement for people, on the top of the requirement for ecosystems, where would you be planting this stuff? Another thing you have to be really careful about whenever you do these schemes is all the little things add up. You have to be very careful about your accounting. So when you harvest the trees, when the trees grow back, when you transport the biomass to the plant, all of those things take energy to get there, right? You can't just drive a semi filled with wood chips to the plant and say, I'm good, I'm carbon negative now, right? And so another problem with these plants is that the capture part is not a solved thing. It takes a lot of energy to capture the emissions from a plant. And in fact, the places where it's actually easier, CO2 plants, coal plants, where they almost emit pure CO2, it actually has not been economical at all. You have to just pay to maintain it. And the problem is that it takes on the order of 15, 20, or 30% of the energy that the plant produces to capture the CO2 from the smokestacks. So you get much more bang for your buck if you can ignore the CO2 leaving the smokestacks. And biomass is much more difficult because biomass burns much dirtier than coal. Coal, the byproduct is almost entirely CO2 in this case that would come out of there. But for biomass, it would be a lot more other gunk. So it's unclear if it's economical. It's unclear how you would calculate all the stages that would prove that you were carbon negative. And so a very famous example of this would be ethanol. And another study came out recently saying that ethanol actually, in a lot of cases, puts more CO2 in the atmosphere than gasoline does, just because it takes so many energy inputs at all the stages of ethanol production to get it to the pump. And I think in a lot of the cases, BECCS is going to be similar, even if you somehow could unlock all of that land. So direct air capture is a lot different from BECCS. It seems like it works. And so this is a really cool plant in Iceland, the Orca direct air capture plant, run by Climeworks, built by Climeworks. And so this plant went live last year. It got a ton of headlines. And it runs off geothermal power, which is cool. It's in Iceland, unsurprisingly. And so what this does, what DAC does, is it has a bunch of fans and it sucks in ambient air and it runs the ambient air over adsorbent, some kind of chemical that grabs onto CO2 in the air. And so then what you do is you have this adsorbent that's rich in CO2 and you heat it up and you pull off the CO2 and you do something with the CO2 then. And so in the case of the Climeworks plant, it injects the CO2 into water, and then it injects that water deep underground into basalt rock formations where it slowly mineralizes. It basically turns into rock. So this is very cool. It takes it out of the air, it runs on clean energy, and it takes CO2 out of the air. The problem with it is that this is sort of the first of its kind plant, and it only removes 4,000 tons of CO2 from the atmosphere a year. And it hasn't even done that yet, right? Because it hasn't even been operating for a year. And to put that into perspective, 4,000 tons of CO2 from the atmosphere a year is about the emissions of 250 average Americans. So, a small-sized town would need, 40 of these things operating to offset the emissions of each of its citizens. And so this is really the big problem with direct air capture, is that it requires a lot of energy, and it's unclear where that energy is going to come from. And so one of the estimates for if direct air capture ever hit the gigaton scale, which is what is required of these things, it might use on the order of half of all the energy used today to power sort of a multi-gigaton scale direct air capture. So just enormous power hungry technology. So a lot of the research in this, of course, is to come up with ways where it doesn't need as much power. And of course, the main power requirement is heating up the adsorbent to strip the CO2 off once it's on there. I think that's the main energy requirement of direct air capture, is that heating element. So if research can somehow make that better, maybe it'll be a little bit more feasible. But for right now, it seems like it will stay sort of a smaller scale technology. Another interesting one is called enhanced weathering. And so weathering is a natural component of the geological carbon cycle that works over millions of years to remove atmospheric CO2. So in the geologic carbon cycle, what happens is that CO2 gets absorbed into rainwater and forms very weak acid, carbonic acid. That acid falls on silicate minerals, and that CO2 binds to the rock and washes away in rivers and eventually out to the ocean, where it falls to the bottom and then gets subducted in the plates. And that's sort of the way that the geologic carbon cycle closes. And then it gets released very slowly again by volcanoes. The problem with this part of the geologic carbon cycle is that it's very, very slow. It's a thing that, takes millions, tens of millions, hundreds of millions of years to work. And so the idea is to speed up this part. The problem is that sort of the demands of the chemistry just mean that it probably won't happen. So two proposals are shown here in the picture. On the left is shown Project Vesta olivine beaches. So they're taking a silicate mineral called olivine, they're spreading it crushed over small beaches, and the wave action is meant to expose the olivine to the air and to the ocean and suck CO2 out of the air and the ocean. And so they're measuring that right now to see how effective it is. On the right is called is carbon drawdowns proposals. They're doing this at a bunch of fields in Europe. and they're spreading crushed olivine and basalt on farm fields. And the idea is that farmers could spread this kind of rock dust instead of limestone when farmers treat their fields. And both of these are cool. The chemistry is cool. The applications are cool. It seems like improvements can be made. But the big problem with them is in this quote and the second bullet point on the page. And so this is from Dr. Ken Caldera, a former Stanford professor, a longtime climate researcher. And what he says is that the mass of silicate mineral required is about an order of magnitude larger than carbon mass. To offset the emissions of a single American would require grinding and transporting about 250 pounds of silicate rock per day. And so you could probably reduce that order of magnitude difference, with a little bit of clever, engineering and technology. But the problem, again, is all the accounting of the little steps. You have to mine the rock. You have to crush the rock. You have to transport the rock. And even then, you have to expose the rock to the air. And it takes a long time for that rock to be exposed to the air. And so it takes a lot of rock to suck CO2 out of the air. And it really doesn't seem like this will suck CO2 out of the air in a really significant way at a gigaton scale. So those are three sort of engineering kind of solutions, but there's also kind of natural solutions, things like replanting forests. So planting trees is probably the biggest and most successful carbon removal strategy to date. And so the main one is called reforestation. And so this is replanting lost forests, bringing former forests back to health. And one of the problems with that is shown in this graphic here. So last year, there was a bunch of fires in the West, as there is every year now. And one of those fires in Oregon, called the Bootleg Fire, actually burned a significant amount of a carbon offset forest. So the state of California has relatively ambitious climate goals. They've been buying carbon offsets from all across the United States. And one of those offsets was called Project ACR 273 in South Central Oregon. And the fire burned through. And all of that carbon that California had been planning on assuming would be out of the air, at least for 50, 60, 80 years, all of a sudden went back into the air. So California still did, the emissions that it was planning to do, and the thing that it bought to offset its emissions didn't even work. And this is one of the big problems with natural negative emission technologies, is it's unclear how permanent they are. And so there's lots of questions, as biomes shift, what's the new forest that you plant here? So here in Minnesota, where I grew up and where I live now, a big question people are asking is, what type of forest will be able to survive where I am? So generally speaking, the forests are marching north and a little bit to the east. So the places where, there used to be more northern forests, more conifers, is going to dry out a bit, and will likely be things more like oaks and maples will be happier. And places that used to be more oak savanna will be more suitable for what would be prairie, if we were able to coexist with prairie. And so as biomes shift, what do you plant? What's the right thing to plant? Of course, as I've been saying, are forests too vulnerable to wildfire to be considered sinks? If you look at a tree, how certain can you be that, that a forest is going to be there in 100 years? With the huge increase in wildfires, in tree pests and tree diseases, and things like that. Of course, if you're somewhere like the Amazon, tree clearing is happening at a very fast rate as well. Another question you could ask is, how fast does this sequester carbon? If you plant a tree, it'll grow very slowly. It'll grow faster and take more CO2 out of the air for a bit. But a tree needs a long time. An old growth forest takes a really, really long time to come to maturity. It's not something that you can just plant and sit back. It's something that takes a lot of work. There's other natural solutions as well. There's something called afforestation, which you need to keep in mind as compared to reforestation. So afforestation is planting forests where there didn't used to be forest. And so the question with this is that, are you just planting trees to suck CO2 out of the air? And in this case, you're not planting trees to restore ecosystems, right? You're not planting trees so that woodpeckers, can be happy, bears can eat acorns. You're just planting trees so that you can tell someone that you took CO2 out of the air. So a lot of the times, this is sort of a dead-end solution. It's not one that really thinks about the larger picture and things. Soil is one that people get really excited about, but I have a hard time thinking it's going to be that big of a solution. Generally speaking, what people are hoping for is farming practices that rebuild carbon-rich topsoil. Things like no-till, and also adding things to the soil, carbon amendments like biochar. There's also things like having farm fields that coexist with native ecosystems, prairie stripping, and buffer zones. So this has tons of co-benefits as well. It slows down flooding because it goes back to sort of what the landscape more used to look like. It slows down soil erosion and soil loss, and it provides habitat for things like pollinators that can survive on narrow strips on native plants. The question is, how fast does this sequester carbon? It took so long for soil to build up in these places. It's unclear if you can just very quickly restore it. And a lot of the claims that you can, I think, sort of fall when they're looked at closer. And I think this is one of the situations where the benefits need to more be away from the carbon side. We should be doing them so that you use less fertilizer, so that there's less soil loss, so that flooding isn't as bad. We should not do them because we think that the soil amendment practices are going to suck a bunch of CO2 out of the air very quickly. We can't just rebuild soil instantly. And of course, general ecosystem restoration, if we back out, restoring, bogs and swamps, restoring riparian areas, riverside ecosystems, restoring prairies, restoring mangroves and coastal ecosystems. Doing all of these things are so good, but it's unclear if they're going to, suck gigatons of CO2 out of the air. We should just do them for ecosystem restoration. We should not do them expecting some big CO2 removal pat on the back. It's just unclear how fast they take CO2 out of the air. It's unclear if they're permanent CO2 removal. So if you're thinking about these negative emission technologies, how big do you want them to get? How significant do you want them to get? So let's ground ourselves in the sort of one of the big numbers of the carbon cycle that's affected by human activity. So think of the CO2 in the atmosphere as the level in a bathtub, and the faucet of the bathtub is all the CO2 that we add to the atmosphere each year from fossil fuel burning, from land clearing, and things like that. And so generally speaking, we add about 40 gigatons of CO2 to the atmosphere a year. But not all of that 40 gigatons of CO2 sticks in the air every year. On average, about 10 gigatons of CO2 is taken up by the land, and about 10 gigatons of CO2 is taken up by the ocean. So 40 is added, 20 is removed. That means the amount in the bathtub, the amount in the atmosphere goes up by 20 each year. So every year we keep emitting CO2, the amount of CO2 in the atmosphere goes up. The ocean and the land are only removing our excess, right? And there's every reason to believe that the percentage that the land and the ocean can take up will decrease in efficacy going forward. Things like the Amazon getting cleared, wildfires in Western North America, tropical forests under threat from a variety of reasons across the world. I guess wildfires, in Siberia, all the way in the Arctic, everywhere in the world. All of these reasons are reasons to think that the ecosystems that we used to rely on to suck CO2 out of the air just won't be as strong as they used to in the past. So those are sort of numbers to think about. We put 40 gigatons of CO2 into the air on average each year, and the land and the ocean take up about 10 gigatons of CO2 on average each year. So this is an example of the output from a sort of a a planning model from one of the climate reports. And what this does is give a future below 1.5 C warming. So this shows global carbon dioxide emissions. So on the left, you can see reaching our current peak around a little over 40 gigatons of CO2 a year. And so under this plan to reach 1.5 C warming, we reduce our emissions 90% in the next 40 years. And by the end of the century, we are sucking out 10 gigatons of CO2 a year out of the air. So, these plans that have us stay under 1.5 C warming assume that we can develop these technologies that I just talked about on the order of how much CO2 all of the land in the world and all of the ocean in the world take out of the air. So this is the ambitious scale that people are imagining. 5 to 10 gigatons of CO2 of carbon removal by the end of the century. So just really incredible CO2 removal by the end of the century. So on the scale of all the world's ocean CO2 removal. So even if you say you develop these technologies, say we had some breakthrough in direct air capture is 10 times cheaper, 10 times easier to do. Does that mean that we're going to transition to the renewables economy really quickly, in the same world that we're in? Probably not, right? So you have to get your priorities straight first, even if these technologies work. And so this is a very good example 3 years ago of that. An Italian oil and gas company bought a bunch of plots that they paid someone to reforest, and basically that was supposed to offset operations emissions from their oil and gas business. Basically the emissions it took them to drill for oil and deliver oil, not the emissions of the actual burning of the oil and gas, but the emissions it took to get the oil and gas to market out of the ground. So, you have to get your priorities right? You have to do, if you're going to rely on negative emissions technologies or not rely on negative emissions technologies, the backbone of what you do has to be decarbonizing, right? The negative emission technologies are just going to be icing on the cake. The background of everything is emissions reductions. It's stopping burning fossil fuels. So let's go through these examples of technologies that I covered. The first was bioenergy with carbon capture and sequestration. And the negatives I see with it are enormous land, fertilizer, and water requirements that will compete with local needs for those things. It's unclear if the capture technology can be made to be economic. It would take a lot of subsidies to make this even economical at all. And for example, with ethanol or wood pellets, which is in an example of that is in one of the articles that I put into the Google Drive folder, it's going to take very careful accounting to determine the entire production chain's true carbon footprint to prove that it is carbon negative, or carbon neutral even. Direct air capture and sequestration, basically it just takes a butt ton of electricity, right? You have to heat these absorbents to strip off the CO2, and the costs are just huge. And that's its big thing, is that it just takes tons and tons of energy. And of course, as we know right now, lots of things are competing for energy. Lots of things are competing for electricity. And so if you added this enormous new industry that required tons of energy, what would have to be dropped to the side for that? And so one thing I didn't talk about as much, I don't know as much about it, is the geologic reservoirs for the carbon, where you're going to pump all this CO2 once you've captured it in liquid form. And so part of the reason the Climeworks plant in Iceland is misleading is because it has a basalt reservoir. And from talking to some people who know much more about geology than I do online, it seems like that's kind of a special case. Not every place necessarily will be able to accept lots of CO2 pumped into it. And so, of course, we have lots of examples where pumping stuff into the ground endlessly doesn't turn out well. And so I think we should not take that side of things for granted, that we just would be able to find all these places to pump stuff underground also. A third one I talked about was enhanced weathering. Maybe it'll be a fine sort of very small solution at some point, but mining, crushing, transporting, and the simple requirements for how much rock you need means it's never going to scale to a gigaton level solution. And I think natural negative emission technologies, they're amazing as ecosystem restoration. You should never stop doing them, but you should never do them because they're carbon removal. You should plant a forest because you love forests. You should restore a prairie because you love prairie, and you love the butterflies that land on the flowers, right? You should not do it because it maybe offsets like 2 days worth of your carbon emissions, And so just the last bullet point, these technologies may eventually be useful in targeted applications, things like, offsetting hard to decarbonize cement emissions, right? These small things that we're going to need as we move to renewable economy, but are hard to decarbonize themselves. Maybe they'll be applicable in these small targeted areas. But I think at present, the only technology that still has a very small chance of getting to the gigaton scale is direct air capture. I think the other ones are all going to be sort of niche applications at best. And the only one that still has a chance is direct air capture. And I think that is very faint. I don't think that is anything to rely on. So let's get to the second part. So say global warming is bad. It's going to get worse. People are freaking out, understandably. It turns out we can't just easily suck CO2 out of the air. People start to panic, understandably. What if we did something else to keep the planet livable, right? What if we started to block the sun? And so that is a whole series of ideas called solar radiation management. So the idea basically is if we can't reopen the greenhouse, the atmospheric window, if we can't take greenhouse gases out of the air, what if we make the planet brighter? What if we increase the albedo of the planet? So I've added a third weird looking arrow here, basically meaning that we're reflecting more sunlight into space. We're letting less be absorbed by the climate system. So this is solar radiation management, which is a very funny clinical name for something so crazy and ambitious. So the idea of solar radiation management, the idea is basically, say it's 2035, the effects of global warming hit us faster than we thought. A 1.5 C world is more deadly than we thought. Sea level rise is bad. Heat waves are horrible. Flooding rains are horrible. Droughts are horrible. Crop failures are horrible. And finally, the world gets its act together and says, okay, we're all going to work together. And we're finally going to confront this. We're finally going to follow, what the IPCC says that we should do, all this kind of stuff. But they say, if we let warming continue, we're going to need energy to decarbonize. We need to buy ourselves time. And so the future where we didn't do anything, we kept burning fossil fuels is in red on this graph. And basically climate stuff just gets worse. All of those things I talked about keeps getting worse. If we aggressively cut emissions, we would lower climate impacts, right? The less CO2 we put in the air, the less bad things happen. But the worry is that we won't cut emissions aggressively enough, right? And so we might enter this period, say 2040 to 2080, where emissions are, where global temperatures are approaching 2C and then for a bit go over 2C. The idea is that the whole world working together decides, let's say for 40 plus years, while we develop negative emission technology that doesn't exist yet, let's cool the planet so that we don't have, planet-wide crop failures, so we don't have terrible floods, so we don't have terrible droughts. And the idea is to sort of minimize climate impacts for a key number of decades while we develop technologies that suck CO2 out of the air, while we develop the economy that runs on sunlight and wind instead of on fossil fuels. So what solar radiation management is supposed to do is buy us time for these technologies that I just talked about to come to fruition. So how should we cool the planet? What is the best way to cool the planet artificially? And so the hint that people have taken is from volcanoes. And so this is a graphic from change in global average temperature, 1880 through a couple years ago. I made this graphic a couple years ago just because we're looking at volcanoes, so it doesn't need to go through the present. And it shows 5 of the biggest volcanic eruptions from a climate perspective in the last 140 years. Pinatubo, El Chichon, Agung, Santa Maria, Krakatoa. All of these, if you look at the global average temperature, for 1 or 2 years after these eruptions, global average temperatures plummeted. And so what volcanoes do is that they release what's called sulfate aerosols into the stratosphere, precursors to sulfate aerosols. And so this is little haze, kind of like the crap you see on a gross summer day near a city, the haze in the air, similar to that. This is a haze that instead sits in the stratosphere. And since it's in the stratosphere, it's above most of our weather, and so it can survive there for 2 years, 1 to 2 years. And while it's up there, it acts as sunblock for the climate system. It reflects sunlight back to space. So as it does this, as it reflects sunlight back to space, it cools the planet, of course, because the planet is absorbing less radiation. And this effect lasts as long as those stratospheric aerosols last, and eventually gravity settles them out of the air. And then when they get down to the troposphere, they get quickly rained out in a matter of weeks, and the climate effect vanishes. So the idea from a solar radiation management perspective, from a trying to keep the climate livable perspective, is to basically have a permanent Pinatubo, to permanently cool the planet 1 degree C or so, kind of forever. And so this is a really great paper from Alan Robach, who's at Rutgers. And this is a very funny cartoon that was the cover, of course, for the talk. And you can see sort of 4 proposals here for putting sulfate aerosols into the stratosphere. So going from left to right, the idea is to get these howitzers that can shoot sulfate aerosols into the stratosphere. So just a bunch of cannons all over the world that are always shooting dust into the air. Having a 10-mile high tower. The idea would be to build it on the Greenland ice sheet, because generally speaking, that's sort of the highest flat place that you can get to. And then the tower, I think, only needs to be 5 miles high. I think that's what it is. Airplanes, and so the airplanes would have little nozzles that shoot out sulfate aerosols. And then the 4th one is something like balloons. You basically send balloons up to the height where they would explode, and then they would deposit a payload of sulfate aerosols. So it turns out this is a really fun paper to read. If you like reading papers, it's not too scientific. It basically just looks at all these schemes and prices them out, looks at the engineering issues at hand. And basically what they said is that looking at all these carefully, the only one that makes sense is airplane. And an airplane system is actually quite cheap. So on the order of 10, 20, $30 billion a year once the system was developed. So the only real technical issue here is developing some sort of the nozzle that can spray the sulfate aerosols. There's some chemistry problems involved there when you're up in the stratosphere trying to spray that much of a given kind of aerosol. But it seems like with targeted research, it could be overcome. And once you did, it would be relatively cheap to retrofit jets and a fleet of jets that would sort of always be flying around spraying this dust in the air. So really on the order, the way we think of the military budget, the way we think of sort of money in America at the federal level, 10 or 20 billion dollars, really isn't that much. So I think a very important thing to remember about solar radiation management is that it is financially feasible. We probably could do it with some targeted research. We could probably have this program off the ground. That's a very important thing to remember. The more important thing to remember, though, is that it is a crazy idea for a lot of reasons. And so this is a fun graphic that I found from a study that came out this month, very new. And basically it looks at sort of the chance of something happening versus how damaging it could be for a variety of secondary effects of stratospheric aerosol injection or solar radiation management. Basically the planes flying around and shooting dust that blocks the sun in the stratosphere. So let's look at a lot of these. A very famous one here is on the left middle, diffusion and dimming of light. And basically what people say is that the sky will be sort of hazy and milky all the time, right? You can think about the days when pollution doesn't blow out of a city and just kind of lingers, just kind of that gunk in the air, the directionless light. That's sort of one of the side effects of this. The effect of sulfate aerosols on the chemistry of the atmosphere is pretty significant. It will actually deplete stratospheric ozone. So we've made all this progress with decreasing use of CFCs, and sulfate aerosols would undo a lot of that progress. And as sulfate aerosols rain out, in a related thing, so you're pumping a bunch of sulfate aerosols into the air. You're pumping enough that it stays in the stratosphere, but the atmosphere, what's called the Brewer-Dobson circulation, high up in the air, deposits stratospheric air and these aerosols at the in the Arctic and the Antarctic all the time. So it's always dropping stuff from the stratosphere into our part of the atmosphere. And basically what this means is that you have this very acidic thing, the precursor to acid rain, this sulfur in the air. It would be falling on very delicate Arctic ecosystems. So you'd be generating a bunch of acid rain in high latitudes by this. You'd be storing ozone and generating acid rain. One of the things that scares me the most is regional precipitation changes. Every time you sort of ding the climate system, you get a response. And we basically don't know exactly what the regional changes are going to be because of this until we start doing it. So you can imagine, say somehow miraculously the world agrees to do solar radiation management with the goal of cooling the planet 1.5 degrees, over the course of 20 years, and then working on decarbonization and emissions removal. What if after 10 years, after the program was well underway but was not, at full power, what if all of a sudden the monsoon failed in India or in East Asia, and those places couldn't grow any of the food that they expected? Could you blame it on the geoengineering? Could you unravel the causes? You couldn't really. You couldn't point your finger specifically at it because there was too many things changing at once. So you can imagine the first time something went wrong, you would have people very, very, very mad at this thing that they would blame for it happening. These huge regional precipitation changes, and just like there would be places that would get drought, there would be places that would get flooding rains as well. So you'd be subjecting people to these regional climate shifts if you did that, and you'd have to prepare for it. You have to either move people to a place where it's safe. You'd have to commit to supporting them, things like that. That you couldn't just do. It's not necessarily true that the climate is going to be safer for everyone immediately. There's going to be these regional changes as well, overlaid on the cooling. And I think sort of along with that is international conflict, right? I think that covers up a lot of stuff. And the thing that makes me most upset about the idea of solar radiation management is that literally all of the world would have to get along for it to work, right? Because all it is just jets flying around. I don't even think the United States unilaterally could decide to just keep flying jets around the world, injecting stuff into the air, right? I don't think the rest of the world would agree to that. And so then, of course, as we're thinking about now, sort of what the next steps of that are. And of course, the biggest shock, the biggest thing that people think about, the biggest threat is what's called termination shock. And so this is what would happen if you suddenly stopped doing solar radiation management. So that's the name of a Neil Stephenson book that came out last year, sort of detailing what would happen in the case of a solar radiation management scheme suddenly ending. And so let's look a little bit more at termination shock. So this is showing termination shock. In a study from about 10 years ago, so on the left is showing change in near surface air temperature. And so we have a few scenarios. So in black is warming up to the present. The red is warming under a very high warming scenario. Again, it probably won't get that bad, but this is just for academic purposes. And the blue shows what if in 2035 we started doing solar radiation management and we started gradually cooling the planet back to, about the 1980s average or so of climate. So instead of it going up to warming, we do this cooling. And so the idea is that you're cooling the planet, but you keep using fossil fuels because you're cooling the planet now. So the warming side of things is not as big of a deal. And so then what the study did was said, what if solar radiation management ceased in 2060 all of a sudden? What if the world said, I don't want to do this anymore? What if a president came along and said, this is bogus. Why are we paying for this thing that helps the rest of the world? They need to pay up. All of a sudden the planes stop flying. Let's say someone shoots down the planes, all these, reasons that the program could suddenly stop. People just decide to give up. They have short memories. All of a sudden, the warming that's been bottled up, decades of warming, would be unleashed mostly in 5 years. And so, as I've been trying to say several times now, is that one of the reasons why anthropogenic global warming is so bad is because of how fast it's happening, right? And that's the speed of what's here on the left of the graph, this speed, about 0.3 degrees C per decade. This would be on the order of multiple degrees in a decade. This would be so fast and so horrible. I think civilization as we know it would not survive. And so this is termination shock, this return to the sort of unmasked warming of the greenhouse gases that you've put into the air. So this sudden jump back to the warmer climate. And so that is what termination shock is. And so one of the readings that I put into the folder is by Ray Pierre Humbert, a professor at University of Chicago. And so what he basically argues is that once you start doing solar radiation management, you can't stop. And part of the reason it is because of this threat of termination shock. And so what he calls it is the millennium commitment. Basically, if you start solar radiation management, you cannot quit it because of the threat of termination shock. And one of the things that underpins it is that he, similar to what I argued here, does not think that negative emission technologies will let us suck, hundreds of gigatons of CO2 out of the air, as is required by some of these schemes. So the only reason that you would do solar radiation management is to buy yourself time to develop and deploy negative emission technology. But if the negative emission technology never shows, then you are committed to doing solar radiation management essentially forever. So you can imagine handing off a project that needs to go 50 years, 100 years, all these things. Could you imagine what the world would look like to have to hand off a project 100 years into the future, a highly technical project? It's very hard to imagine for me. And so for this and for even other reasons, I find solar radiation management to be an extremely flawed idea, a dangerous idea. And really to wrap up, these are my last few slides. The only thing we know works is stopping emitting CO2. That is the only thing that we know works. And so this graphic here shows a fundamental relationship in climate science, which is the amount of CO2 put into the air has a linear relation to how warm the climate system gets. And basically, we've put in about 2,500, 2,600 gigatons of CO2 into the air. And as we keep adding to that going forward, it'll just get warmer and warmer. So the more CO2 we put into the air, the warmer it will get. And so knowing that, one thing that scientists have done, and people who think about this, is they say, let's set an upper limit on how warm we want it to get. And so one thing that came up with in 2018, there was a special report to look at keeping warming to 1.5 degrees C. And so we've always talked about 1.5 degrees C as a target in recent years. And this graphic basically shows why it's too late to keep warming to 1.5 degrees C. So historic emissions are here in black, as you can see, and a path of emission changes starting this year that would give us a 50% chance of staying below 1.5 degrees C is shown in this heavy gray. And you can see we basically zero emissions before 2050. Before the end of the century, before the end of this decade, we essentially half emissions. And the other lesson of this is if we had started earlier, if we had started in the year 2000, we would have only had to reduce our emissions about 3% year over year. And if we keep emitting at the level we are emitting for another 10 years, we'll essentially have used up the 1.5C budget. So the longer you wait to act, the faster you have to act. This is a fundamental truth of carbon budgets and climate action. And basically, we would have to act quicker than any sort of, society or government has shown a willingness to act, I think, at the national stage. To hit the 1.5C target. So basically sometime this decade or early next decade, we will have locked in 1.5C of warming, it seems like. And you can imagine the 2C degree budget basically looks like this, but the slopes are not as steep. But the longer we wait to act, the harder it will be to hit the 2C deadline as well. This is a really nice graphic that Dr. Glenn Peters made and put on Twitter recently. And shows historic emissions on the left of emissions from burning fossil fuels. And basically what he shows are three things in the future, three ways of framing the future. The orange is where we said we would go, sort of in all the pledges that people make, the NDCs, all the countries they said, this is what we're going to try to do. This is where they said they would go. Where we should be going if we want to have a chance at below 2C of warming, at 1.5C of warming, if we were so ambitious, is we would be at zero fossil fuel burning by 2050. But where we really are is up here. This is where countries, based on, what industries they're supporting, where power systems, are planning to get their energy, oil, gas, and coal, all these things, this is what is really the world looks like, right? So there's this huge gulf between what we say we'll do and what we're actually doing, and this even bigger gulf between what we're doing and what we should be doing. And the scale of things like negative emissions technologies, they would only shave off the smallest amount between what we are doing and what we say we'll do. Almost all of the work is stopping burning fossil fuels. That is almost all of the work of any climate action. All the other stuff is important, but the backbone of it, the thing that holds all the rest of it up, is stopping burning fossil fuels. That is the backbone of it. That is the reason we got into this, and is the thing that will have to end to have any shot of getting out of it. So, have to end a talk with a bunch of bullet points. Here is my second to last slide, but my last content slide. There's only one thing we know works, and that's stopping emitting CO2. So a thing I hope you understand, and I think all of you do, is there's no safe level of additional warming. We're already experiencing harmful impacts at 1.3C of warming. 1.5 and 2 is going to be even worse, right? The warmer it gets, the worse it's going to get. And so because we haven't, moved off of fossil fuels, scientists and engineers have come up with creative proposals to limit warming for a world that refuses to move off of fossil fuels. And at present, ambitious proposals to take CO2 out of the air seem likely to fail to meet this 5 to 10 gigaton CO2 a year scale that's required by these energy models. The expense, the energy demand, the land requirements, the resource requirements are significant hurdles to nets. But the thing that's important to remember is even if negative emission technologies become cheap, we still have to burn fossil fuels. We have to stop burning fossil fuels, sorry. We can't emit and remove 40 gigatons of CO2 a year, right? In our wildest dreams, if humanity takes some quantum leap in cooperation and empathy for each other, all these things, we could maybe remove 2 or 3 gigatons of CO2 a year. In our wildest science fiction dreams, there's no way that we can emit and remove 40 gigatons of CO2 a year. We still have to stop burning fossil fuels. Negative emission technology will sort of be the icing on the cake of that. So unlike negative emission technologies, which act to lessen the cause of global warming, they take greenhouse gases out of the atmosphere. Solar radiation management only alleviates the symptoms. And the simplest proposal for geoengineering, spraying sulfur aerosols in the stratosphere with specially designed airplanes, is extremely cheap, especially compared to the damages of warming. So it seems like it is something that we could do if we wanted to. So this is one of my problems. Another one of my problems is solar radiation management. We currently need to engage in one global mega project, decarbonizing the world economy. And that's one we are completely failing on doing, right? But if we did solar radiation management, we would jump from needing to do one global mega project together to 3. we'd have to do decarbonization, which we're failing to do right now, carbon dioxide removal, which may never be possible, and solar radiation management, which is this very tricky technical thing that everyone would have to cooperate all the time for decades to work. So researching negative emission technology, I think, is a great idea, and there's lots of money in it, of course, unsurprisingly. Lots of people are funding it. Deep pockets are funding it. And while researching them is a great idea, relying on them to someday exist at scale is not a great idea. Solar geoengineering, on the other hand, I think has unsolvable flaws that mean it should not be proposed as a serious solution. And personally, I do not think it should even be researched. But that is maybe a bit of a spicier opinion that we can argue about. Thank you, everybody, so much for coming. You know where to reach me. There's a link to my slides and some suggested further reading. I'll drop that back in the chat. And again, I have this Patreon if you like the way I think about these things. Thank you so much for sticking around. It looks like I talked for almost exactly 90 minutes. Thank you, everybody, for coming.